Alright class, today we're going to talk about GC, gas chromatography. Now before I give you a lecture about how to use GC and what it is, I want to talk about why we use GC and what type of information is going to give us that is going to be useful. Here's the information it's going to give us. GC will give info on two things that are useful. Number one, is going to give information on the composition of a mixture. Now what does that mean? Composition of a mixture, it means it's going to give us information of how many different compounds are in our mixture. So you have a mixture, you want to know how many different types of compound are present in this mixture. Okay, so mixture, they have 2 compounds in there, 3 compounds in there. Basically, how many different compounds are present in this mixture. Now, the second piece of information that it's going to give you is the quantity. Is the quantity of each compound. So what does that mean? So, for example, I'm going to use a GC. It's going to tell me that my mixture has 2 compounds, A and B. Then the quantity is going to tell me I have 60% A and 40% B, for example. Okay, so this is why it's useful to use GC. We're going to figure out how many compounds in our mixture and then what's the percentage of each compound in that mixture. All right, beautiful so far. Now let's talk about what a GC actually looks like. This is a GC, gas chromatography. It took me a while to draw this. It looks simple, but it is not simple. It looks kind of beautiful though now, huh? So here's my GC. I want to go over what happens and then how you inject your sample. So you are going to have your sample, your mixture. What you're going to do, you're going to take about 2 drops of your sample and you add it to 2 ml of solvent. So it's going to be very diluted. So 2 drops of your sample in 2 ml of solvent. Then what you're going to do, you're going to inject it here through the injection port. And when we inject it, we usually have 1 ml of air in the syringe, 1 ml of sample in the syringe, and 1 ml of air in the syringe. So the sample is sandwiched between air in the syringe, and then you are going to inject it here. Again, we're going to show you in lab exactly how to inject it. Now, what happens once you inject it? Once you inject your sample using a needle, because this is really, really hot, it immediately gets converted to the gas phase. And then what happens is we have this helium gas, and the helium gas is going to transport your sample through the heated column. Alright, so again, you are going to inject your sample. This is really, really hot. So as soon as you're injecting your sample, immediately your compounds are going to get converted to the gas phase. And the helium is going to push them and transport them into these heated columns. Now, the compounds that have a higher boiling point, they're going to elute slower. They're going to have a longer retention time to get to the detector. And then what a detector, then you're going to have a recorder, then you are going to get a graph that looks like this. Basically, you're going to get peaks. Now, these peaks, they give you 2 pieces of information. So these peaks, they give you 2 pieces of information. The first piece of information they give you area percentage. And the second piece of information the peaks give you, they give you the retention time. And we're going to go over what those are later and then how to use them. So, okay, you're going to inject your sample. It's going to go through over here, get to the detector. Then you are going to have a graph. And you're going to get these peaks. And these peaks have 2 pieces of information. Area percentage and retention time. Okay. Now let's say you have a mixture and your mixture has 2 alcohol. So far so good. Let's say you have a mixture and your mixture has 2 alcohol. here's my question for you. How many peaks would you expect to get when you run it through the GC? What do you think? Okay, so you have a mixture. Your mixture has 2 alcohols. You expect to get actually 3 peaks, because 1 peak is going to be the solvent peak. Don't forget that, right? We have a solvent, and our solvent is actually a majority of our sample, because we had 2 drops in about 2 ml of solvent. And then for the first alcohol, you are going to get a peak, and for the second alcohol, you are going to get a peak. So how many peaks do you expect? You are expecting to get 3 peaks when you run your GC. Okay, it's kind of good to know what you're expecting. So we're expecting to get 3 peaks when you run your GC, not JC. Now, remember what kind of information you get from the peaks. We talked about the kind of information you're gonna get. You're gonna get area percentage, and you are going to get retention time. These are the 2 pieces of information that you are going to get. Now, let's look at a possible graph that we might get from your sample. So we have a mixture, and we said in mixture we have 2 alcohols, and of course you are going to get a peak for the solvent as well. I'm going to ignore the solvent for now. So here are the 2 peaks I'm going to get for my mixture of 2 alcohols. Now, when you get a peak, 0, that is basically when you inject. Okay? So that's basically when you inject. Now, what am I going to look for this? Remember, we said that you can get area percentage and you can get the retention time from the graph, right? So, based on that, basically, if I go height times the width, what I'm going to get the area for each peak. Okay, so I need the height and I need the width to get the area under each peak. Now, how am I going to do that? Well, it's easy. If you look at these 2 peaks, let me look at the peak on the right or the left, doesn't matter. So this would be the height. That would be the height. Okay. Now, what's going to be the width? The width, you look at the width at half point. We should be about here. Okay. That would be the width at half point. Okay. So the height times the width is going to give you the area for each peak. Now, what does this mean? What is this going to give me? What kind of meaningful information am I going to get from this? Here's what you're going to get from this. I want to write this down. I want to make sure you're following me. The area under the peak. The area under the peak is proportional to the number of moles. Right? We're doing chemistry. You got to bring the moles out. So the area under the peak is going to tell you is proportional to the number of moles. So the molar composition can be approximated by comparing relative peak areas. I'll repeat this again. So again, you're going to get a graph. And in our case, we said I'm going to have 2 alcohols in the mixture. One is going to be solvent peak. We're going to get to that. For my compounds, I'm going to get 2 peaks for my alcohols. Here's a sample graph that I could get. Here are my 2 peaks. Injection would be 0. And then these are my 2 peaks for my alcohols. And the way I look at it, I looked at the area for each peak, which is the height times the width. And I take the width at half point. And why does the area under the peak matter? The area under the peak matters because it's proportional to the number of moles. And when you have that, then you can figure out the molar composition by comparing relative peak areas. When I compare these 2 together, then I can figure out the molar composition. Again, they're relative to each other. Again, what do I mean by that? Here's what I mean by that. The area percentage of peak A over the area percentage for peak A plus B times 100% is going to give you the percent composition of A. And since I only have two things, I can just subtract it from 100 and get B. I want to name this peak A and name this peak B. Okay? Again, remember, the entire thing is going to end up to be 100 because I only have two compounds in there. So when you compare this, when you compare the peaks relative to each other, you can figure out the percentage of composition. So far, so good? Okay, if I want B, it would be the area percentage for peak B over area percentage for peak A plus B. All right, beautiful. Now, there was another piece of information that this graph can get us. So it was, let's go back here, it was area percentage, it was the retention time. Now, let's go over this retention time. So basically what they do to figure out the retention time, they take the distance for peak A over, again, what's the distance for peak A? Injection, the peak A shows up, over the chart speed. And when you do this, what you end up getting, the retention time. Now, what I really want you to know, I want you to understand what it means, not all these fancy formulas. Basically, what retention time is the time it takes for a compound to go through the GC column. So here I inject, this is the time it takes for A to go through the GC column, and then the time that takes for B to go through the GC column. Now, when you look at these two, it takes longer for B to get through it versus A, which would tell you probably A has a lower boiling point. So this is what retention time is, right? It's just the time that it takes for a solute to pass through the GC column. All right. Now what I want to show you a real example of a GC graph. So here is a GC graph that I actually took a little while ago. If you look at the date on top, it says January 18, 1901. I did not take this in the year 1901. Promise you I'm not that old. So let's go over, this is what you would get if you run it on our GC instrument. When you look at this, do you see these guys over here? Yeah? These are the retention times. Okay? Those are the retention times. So these are my retention time. I'm going to underline it. Okay? Now, one thing that we can do, you could come over here, and RT is for retention time. You could match up those lines to here. So 1.32, that's one right here. That's the first one. And then 1.684, that's the one right here. 1.88, and then 2.989, 4.36, and 5.627. So far, so good. So these are the major peaks that I get. The retention time is like next to them, and I can match them to the retention time down here. So that's the one piece of information we look at. The other one we're looking at is area percent, right? Area percent. Now, when you look at for the peak with a retention time of 1.323, the percent area is 95. What can you tell me about this peak? Based on this, 95% of it is this compound. What is that compound? That is most likely my solvent. Because again, the majority of the sample that you inject is the solvent. And we said you will get a peak for the solvent. And it's usually the one with the biggest and largest area percent. So that is my solvent peak. So when you look at a graph, look at the major peaks on there, there's a retention time right next to those peaks. And when you come to the little table down here, these are the retention time. You can match the retention time here, and you can figure out the area percent for each of these peaks. And it's very important right away figure out which one is a solvent peak. And it's usually the one that area percent is really, really large, because the majority of your compound is the solvent. Yeah? Okay. There is a correction that you would need to apply, and we'll talk about the correction factor later. But right now, I just wanted you to get used to seeing a GC graph. That you see a GC graph, you go, okay, these are my major peaks. I want to come here. Retention time is what I'm after, and the area percent is what I'm after. And I'm going to figure out my solvent right away. Now also, based on this, whatever mixture it was that I took a GC of, you can say there are 1, 2, 3, 4, 5 compounds in that mixture, right? There are 5 compounds in that mixture. All right, beautiful. Nice job. Again, there is a correction factor that you have to apply, but we will talk about that later.